So let's move on to another concept, which is orthogonal matrix, right? So if we consider an orthogonal matrix, which is also representation matrix, we know that if a matrix is an orthogonal if its transpose is equal to inverse, and this is a property that we have defined previously, that if you know a matrix is an orthogonal when if its transpose is equal to the inverse of it. Okay, so what we are going to do is we are going to import this inverse, right? And what we will do is similar to the matrix that has been defined here. We define a Q matrix which has the entry of 1 divided by root over 2, square root of 2, minus 1 divided by square over 2, and so on. And that's what you see in the first line of command here. We are defining a matrix Q which essentially has those 4 elements. Okay, and then using this inverse I and V, which is a function in NumPy, we are taking the inversion of the matrix Q. So so we can see the command which is print in round parenthesis. What we are printing? We are printing the inverse of Q, and then we are also in the next line we are printing Q dot capital T, which is the transpose of the Q matrix, and we want to verify both of them are equal. If both of them are equal, then essentially Q is an orthogonal matrix. So to verify whether a matrix is an orthogonal or not, first thing that you need to do is you need to take the inverse of that matrix and you need to take a transpose of that matrix and see whether the transpose is equal to the inverse of the matrix or not. So let's go ahead and execute this line of command and see whether we get that. So you can see when we printed inverse of Q and when we printed Q dot T, which is the transpose of the matrix Q, both of them are exactly the same, right? So this verifies that the matrix Q itself is an orthogonal matrix. So the matrix that is defined here on the top before the code block that you see here is essentially a orthogonal matrix. Now another way or another equivalence for orthogonal matrix is if the dot product of matrix and its transpose is equal to the identity matrix. So if you take the dot product of the original matrix, right, with the transpose of it, that should result in a identity matrix. And that's what we are doing here in the small code block that we have here, where we have defined this operation where we are storing a matrix I, which is essentially equivalent to the multiplication of the Q matrix with a dot product of Q matrix with its transpose, right? So we are essentially using the command that you see, which is I equal to Q dot round parenthesis Q dot capital T. This allows us to essentially implement the operation dot product of Q by Q transpose. And if that is equal to identity matrix, or what I mean by that, if all the elements of the diagonal element of that matrix comes out to be close to equal to 1 and off diagonal matrix comes out to be equal to very close to non-zero, then essentially that will also help us in verifying whether that matrix is an orthogonal matrix or not. So let's carry this out and see what happens. So we have implemented this, which is Q times Q transpose. Okay, and if you see this matrix, entries that we have on the diagonal is 1 and 1, and the entries that we have in the non-diagonal are numerically very close to 0, right? So e to the power minus 17, so it's very close to 0, and so this is another way to verify that the matrix Q is an orthogonal matrix. This is a second equivalence where Q times Q transpose, if that is equivalent to I or identity matrix, then that matrix Q will be termed as an orthogonal. Let's move on to another concept, the concept of sparse matrix. We also discussed this concept, right? Now, it is a type of matrix that mainly consists of 0 values in most of the entries that you have, right? And the idea is, like, rather than storing all the 0 elements, can we store only the elements which are non-zero, and hopefully that will save us a lot of space, and hopefully we will be able to do computation faster. Now it turns out SciPy is the library that essentially allows us to do operations with the sparse matrices in Python. So what you will see is, rather than NumPy, we have essentially importing the SciPy .sparse library, and this is the library that we are calling in the environment right now. And once we have done that, we should be able to do operations, and we should be able to use sparse representation and all the functions that works on the sparse matrices. So let's go through this code block that you see here and see how that could be used to run sparse matrices and so on. So what we have done is, like, we have basically called the SciPy sparse and invited that into the current environment, and you can see we have created a dense matrix using A, which is basically the np.array, which is the numpy way of defining matrices and so on. And we have defined a matrix A. What we want to do is we want to convert this matrix A into a sparse matrix, right? So that will be the representation. And so you can see this command, which basically converts a matrix A to sparse matrix, which is using the CSR method that is out there. So CSR is the method that we will be using. So the line of code, which is sparse mat equal to CSR underscore matrix A, this allows us to basically take a sort of a condensed or a dense matrix A and convert that into a sparse matrix representation. And then we can also reconstruct, right, the dense matrix from the sparse matrix. So the sparse matrix is sparse mat, and then the next line of code, which is basically telling you the function that you should be using to reconstruct dense matrices, is sparse mat dot to dense, and then you have round parenthesis. So that line of command basically takes sparse matrix, which is a sparse matrix, and converts that into a dense matrix, right? And so let's execute this block of code to see what this block of code does. And essentially what we are doing here is we are taking a dense matrix A, we are representing that in the sparse matrix using CSR method, and then using reconstruction method, we are basically converting that sparse matrix back to a dense matrix. That's what this block of code does. So let's execute this block of code and see how this looks like. So we have executed this code. So again, you can see the first is print A. So you can see the matrix A has been printed, and obviously this matrix A is a sparse matrix because most of the element of the matrix A are essentially 0. So we don't want to use dense representation, and hopefully this might be a good case to use a sparse representation of the matrices that you have there. Now when we did conversion of this dense matrix A to a sparse matrix, which has been stored in the variables sparse mat, and when we print out the sparse mat, you can see we have this entries 0, 2, 2, 0, 3, 2, 1, 2, 1, and so on, that you can see in the just below the code block. These are essentially the locations of non-zero entries, and that's what is the representation, or the way to represent a sparse matrix. And then the third block, which basically prints out the dense mat variable, which is taking the sparse representation and converting it back to the dense representation, is shown here in the bottom, where from the sparse representation we have been able to use the command sparse mat dot to dense round parenthesis, and that converts that back into the dense representation. So this is how you can go back from a dense representation to a sparse representation, and again use functions from SciPy sparse library to do various aspects when we are dealing with the sparse matrices and so on.